Well, greetings everybody. So here's a problem that you'll find on our assignment, and I think it's an important problem to do because in addition to being, I guess you could say, a typical calculus problem with a setup, some algebra to simplify things, maybe some trig identities, it's got all the typical things I think that calculus problems have, but in addition to that, there is something that is unique about how we would reduce this integral and solve it. Okay, so there's something different about this one that I want to highlight in the video. But here's the question. It says find the length of the cardioid. R is 5 plus 5 cosine theta. And let's talk about, before we get into the specifics of that particular polar graph, how this works in general. How do you find the length of all or some portion of a polar curve? Well, we have this integral that will do the job for us. R is some function of theta. Polar coordinates have R and theta. And let's say that the curve, or the part of the curve that we want to measure the length of, is marked off from going, say, from angle A, theta is A, over to some other angle B, theta is B. Then we get this integral from A to B. Those are the angular bounds that define the part of the curve that we want to look at and measure. And we do root r squared plus r prime squared d theta. This integral will be in terms of the variable theta. Okay, so that's how it's done. Now, I guess finding r squared with r given wouldn't be that difficult. Finding r prime and then squaring that, maybe that wouldn't be that difficult either. The only thing I think requires some special attention here in setting it up is what should the bounds be? Because it says find the entire length of this polar curve. As I sketched out our setup, then I say, well, you got some piece of the curve that you want to look at, and it goes from theta is A to B. But what should those angles be to track this entire curve? Okay, well, to understand that, I think we'd have to know a little bit about polar graphs and polar coordinates. And I've covered that in some lessons I've already posted. So here I'm going to go straight to what the graph looks like. Here's the graph of 5 plus 5 cosine theta. It looks like that. When theta is 0, you get this point. R is 10. As theta increases to 90 degrees, or pi over 2, the curve closes in on this point right there where R is 5. But then as theta swings from pi over 2 to pi, the curve closes back in on 0 right there. And to go from 0 for theta to pi, I've traced half of that curve. What this question asked me to measure is, what's the distance all the way around here back where you started? So just by a little analysis, I see, well, if I go from 0 to pi, I've got half of it. But if I keep going, as theta swings from pi over to 3 pi over 2, then we get this part of the curve traced. And from 3 pi over 2 back to 2 pi, we get back where we started. Okay, so I could get half of this curve from 0 to pi, and I can get all of it from 0 to 2 pi. Now, because of that, and because of the symmetry, notice in this picture, the upper portion of this curve looks just like the lower portion. They're identical. They're mirror images of each other. Then it looks like I could do two possible setups, okay? Given that this is my general formula, my general instructions for setting things up, either of these could in principle work. Like I could say, look, you could do from 0 to 2 pi. That'll get you from here all the way around back where you started. That will get you the entire length of that curve. Or you could go from 0 to pi, which would get you exactly half of it, and then you could double. So in principle, it seems like either of these would work. But it turns out, because of the way that we simplified this integral once we set it up, we need to use this second form and not this first form. Okay? So here's what I'm going to do. I'll solve this problem with this setup. 2 times the definite integral from 0 to pi. Okay? And then after I solve that, I'll tell you why this first one is no good. All right, so let's do this. Let's make, for this integral here, that second form, the one with symmetry, the one with the doubling, the one with the bounds from 0 to pi, let's start by just getting all the stuff that we need. Okay, we need to figure out what r squared is, and we need to figure out what r prime is, and then square that. So r is 5 plus 5 cosine theta. R prime is negative 5 sine theta. R squared is 5 plus 5 cosine theta all squared. And then r prime squared is 25 sine squared. Okay, so all that, as I found it, r prime squared and r squared is going to go in here with bounds 0 to pi, and I'll double it. So that's going to look like this, and we get something very complicated, which will usually be the case for this type of problem. But then as I look at it, I notice that some trig identities come into play. Like, so for example, I see 25 cosine squared and plus 25 sine squared. That's the Pythagorean identity. You could factor out 25, get cosine squared plus sine squared, but that's 1. So what you're looking at here is 25 times 1, or 25. So you got 25 here, and you got another 25 there. So you got 50. You get 50 plus 50 cosine theta. Let's factor out the 50. Now, we get here, and then we will get stuck. Like, I have to find some way to simplify this square root with the 1 plus cosine theta. 1 plus cosine theta doesn't reduce with roots, okay? So I would have to think of some other identity that could get me further here. So what I'll do is I'll use a form of the double angle cosine identity. So if you look up the double angle cosine identity, one version that you find is cosine 2 theta is 2 cosine squared theta minus 1. And I can get this to do what I need it to do over here. I can rearrange this so that it will reduce what I have. If I add 1 to both sides, I'll get, and I'll switch the sides too, 2 cosine squared theta is cosine 2 theta plus 1. And that looks a little bit like what I have, except for, look at this. I'm going to switch the angles. You see how with the way this is, this angle here, 2 theta, is twice as big as this one there, theta. So I could make this look exactly like what I have. If I said, okay, let's let this angle be theta over 2 and that one be theta. Is the same relationship still true? This angle, 2 theta, is twice as big as that one, theta. This angle, theta, is twice as big as that one, theta over 2. Same relationship. But do you see what this says? Cosine theta plus 1. That's what I have. And it puts that in terms of a perfect square, which is compatible with simplifying the square root. So it's by this kind of trick with trig identities that we get something out of this, turned into something else compatible with the square root that we happen to have. So that will get me here, okay? Now I've got a factor of 50, a factor of 2, that's 100, okay? And the reason why I used this identity in the way I did was because I get something that can be, I can take the square root of it. Like square root of 100, that's 10, okay? But square root of cosine squared is cosine. Square root of cosine squared of theta over 2 is cosine theta over 2. Now I get a much simpler integral. Look at where we started. This was pretty complicated. But by 2 trig identities, I get something that I can solve by u substitution, like so. And there will be my antiderivative. I put my bounds in. I multiply by 2. I get 40, and then that's the answer, and then we're done. Okay? Now, that's how we solve it. This identity might surprise you the way I used it, but now what I'm thinking is I've showed it to you, so when you work a similar problem like this, then you can anticipate needing to use that. Now, let's go back to one of these questions, which I guess is my reason for showing you this problem, is if both of these integrals make sense in principle to solve this problem, why did I use this one and not that one? Why did I say we should use the second one, not the first one? Here's your answer. So, you see this step here where I wanted to take advantage of, say, taking the square root of a perfect square, like the square root of cosine squared I said was cosine. The square root of cosine squared theta over 2 is cosine theta over 2. It's all because of that. There's something we take for granted about that. It might seem that a square root will cancel with a square, such as the square root of 4 squared is 4. That's true. But that actually doesn't work if this number in there was negative. Like the square root of negative 4 squared is not negative 4, because the square root of negative 4 squared is square root of 16. Square root of 16 is not negative 4. Try it with your calculator. Do square root of 16. It's not negative 4. So this sort of thing, going from here to there, only works as long as that thing right there, cosine theta over 2, is not negative. You have to guarantee that it's not going to be negative. And it's easy to see if you got a negative when there are numbers in front of you, but now I got to think, well, cosine of theta over 2, theta is just some angle. And I need to ensure that that's not going to be a negative number. So look at it like this. That cosine theta over 2 has to be greater than or equal to 0. What does that mean for cosine if we need it to be greater than or equal to 0? Well, we need that angle, theta over 2 in this case, to be in quadrant 1. All right. Once it goes into quadrant 2, then cosine is going to be negative, and you can't actually do this step. All right. If theta over 2 went into quadrant 2, then we can't go from here to there, and so we can't finish the problem. Well, not without some other complicating technique. All right. So as it is, I can't go from here to there. So I need to guarantee that theta over 2 is in quadrant 1. What's that look like? Theta over 2 is between 0 and 90. Okay. And if you want to isolate what that means for theta, that means multiplying by 2 across this inequality. Theta is between 0 and 180, or 0 and pi. So that means that as long as our bounds are 0 to pi, there's nothing wrong with doing this. But once you go beyond pi, it won't work. It's like doing that. And so going from 0 to 2 pi takes us out of where we need to be in order for this step right here to work like we need it to be. Okay, so that's the short story and the long story for this one. All right, so I've solved that one, and I've told you about my considerations for how the identities are used. Keep that in mind. And if you see a similar problem about the length of a cardioid, it might be a slightly different equation, but it's still described as a cardioid, then you can expect a similar technique to what you just saw here.